And the focus of this client is around low resource utilization and privacy, and it's built around the new or like semi-new BIP 157 and 8. So it's targeted at mobile resource constrained environments like laptops, etc. So who am I? Cloudhead. I got into Bitcoin in 2017, and I'm just generally interested in light client technology and user sovereignty. And most of my time goes into Radical, which is peer-to-peer code collaboration stack, so kind of peer-to-peer GitHub. We can talk about that after the presentation if you're interested. So why new light client? Well, it's pretty obvious. There's more and more people on mobile. Decentralization is as important as ever or more, and running a full node is still cumbersome, and it's not really going to get much easier. So we need better light clients, basically. Okay, this is a little bit. 1 second. Okay, good enough. So if we kind of look at the space of client technology, on the far left we have something like Electrum, which is it's essentially a trusted third party. Of course, you can run your own Electrum server, but if you don't, you have some kind of vendor, some kind of company or a friend or a community that is running a node. It's great for efficiency because essentially, as a mobile app or as a user, you don't really need to download anything. You just kind of submit a public key or a script or whatever, and you get a proof in return. But in terms of privacy, obviously, it's not great because you're handing over your addresses or your public keys and of course your IP address. And in terms of reliability, I don't think it's good enough simply because it's just one node that can go down. If whatever you're using, the mobile app, the company goes out of business, they shut down their nodes, then you have to find a replacement. So it's not great for users, I think, in that respect. On the far right, you have full nodes, obviously, which are inefficient in that sense, but of course they're super reliable and private. And then in between, you have BIP 37, which is a Bloom filter BIP, which is kind of the first SPV BIP. And then you have BIP 157, which I'm going to talk about here, which is kind of in the middle. And then a little bit further to the right, you have, or quite a bit further, you have U3XO. Taj is here; he can talk about that more. But essentially, you're always trading off efficiency for reliability and privacy. Okay, so talking about the two kind of options that are in use today in one form or another. Again, in terms of sovereign solutions. So BIP 37, which has been around for a while, and if you've ever used something like Bread Wallet or one of those old school wallets, it was BIP 37 based. I think also Bitcoin J and a few others like that. And the idea here is that the user computes a filter for their transactions or their addresses. They submit that to a node, and that node essentially sets that filter on that connection, and then the node only sends filtered blocks back to the user. And the idea with the Bloom filter is that you have some kind of false positive rate, and so your transaction might be 1 of 10 or 20, which is tunable, and that the node you're talking to doesn't know which one is your own transaction, and so that's private. That's the idea, at least. And then, yeah, the user checks with the filtered blocks can actually check things. And then you have BIP 157, which is kind of the new standard, and there it's a little bit different. It's essentially full nodes compute filters, like one filter per block, and these filters are general, which means there's only ever one filter generated per block, and so you can do that computation once. You can store the filters as a full node, and then the user is going to download those filters from you, you being the full node, and check whether their scripts or their addresses or transactions are in the filters, and if so, they're going to request a full block from another node, from a random node. and then scan the block to update the UTXO set, right? So the privacy upgrade here is that you essentially your transaction is going to be one of any in the block versus one of a sort of subset of the block. But we'll see it's even better than that, or worse for BIP37. So the thing with BIP37 is that even though the idea made a lot of sense in theory, it turns out that since you're using a different filter for each peer, right? If a peer manages to collect more than one filter, they can actually compute an intersection which would reveal your scripts or your transactions, the ones you're interested in. There's also other flaws, but I'm not going to get into it. It's well documented. But because of this, kind of people, like I think it was removed from Bitcoin Core even, or disabled, and a lot of people moved away from Bloom filters. And the only thing that was there as a replacement was Electrum, which I talked about, since a very small minority of people run their own nodes. And so, talking about Electrum, the way it works, so it uses SPV proofs, so at least you know that, if a node tells you that a transaction is in a block, they can't lie about that. But of course it leaks public keys, addresses, or you're leaking those to the node, to the whoever's running the node. And it can lie by omission by just saying, hey, there's no new transactions that concern you. And I mean, lying by omission is one of the trickiest things to solve. But anyway, it is a small problem. Right, and Electrum is actually the default in most Lightning and regular wallets today. I would say 90% of Bitcoin wallets work on Electrum, and usually what they do is they will have a default server which they run themselves that your wallet is connected to, and then you'll have the option to set your own Electrum server to a trusted node or some node that you run yourself. Now, recently, or not so recently, but in Bitcoin terms, it feels recent. Neutrino was developed by Lightning Labs, I believe, and I don't know exactly what the impetus was for Neutrino, but essentially, they built this client and they specified its protocol under BIP 157 and 158. And this was added to Bitcoin Core beginning of last year. And one of the cool things with it, and that may be the reason they developed it in the first place, is that Lightning nodes, and I think their Lightning node doesn't need a full node to be able to verify layer 1 transactions. So you can run Lightning plus Neutrino or a BIP 157 client, and that's kind of everything you need, which I don't think was possible with the other BIP. So just about defaults. So I talked about this a little bit. I think first-time users need good defaults. Essentially, having a server configured is not a great default for the reasons I explained previously. But there's a trade-off, right? And there's no one-size-fits-all. And then for more experienced users, ideally we need a kind of solution space, and we need choice so that users can kind of decide which, what trade-offs they're willing to make or not make, right? So whether it's privacy or performance or storage or that sort of thing. And so now going a little bit into BIP 157. The kind of crux of it is this one honest peer assumption. So essentially the threat model, so to say, is that as long as in your peer set one of them is honest, you will have good results. And typically, like clients make maybe around 10 connections or something like that. So you have a pretty high chance that that you're connected to an honest peer. Given that you're connected to a diverse set of peers, and I'll talk about that also. You have good privacy, so that's a good thing. But since there's no header commitment for the compact filters, so these filters that you're downloading from peers, to verify them, you can't just check the block header, unfortunately. You need a very good address book. So you need a diverse set of peers so that you can sort of check that everyone is agreeing on these filters to make sure you're not being lied to, essentially. In terms of the size, there's a filter header chain and a filter chain. The filter header chain is very small because it's just hashes, essentially. So the full blockchain is 20 megabytes. So the filter header chain for everything is 20 megabytes. But then the actual filters are a little bit bigger. Right now, I think for the last 10,000 blocks or so, they're around 20 kilobytes per filter. Blocks that are less full have smaller filters. Usually, like clients will essentially they might keep the last 1,000 or 10,000 filters for rescans and things like that. And essentially, the concept is that we trade bandwidth for privacy, because downloading all the filters, it's not nothing. And so here's an example of the library that I developed, Nakamoto. It's really meant to be super simple. So I don't know if anyone here is developing wallets, but essentially, you essentially you spawn a client, or you create a client, you spawn it on its own thread, then you just wait for connectivity to the network, and then once you're connected to at least one peer, you can start to do things, or you can wait till you're connected to more peers if you choose to. Now, the architectures may be interesting for some people. To keep a small footprint, I tried to essentially have the client not spawn any threads. So this is all under the control of the developer. The API is basically event-based and command-based. So you receive events from the client, and then you send commands to make it do stuff, and you essentially act on events. I'll kind of show what those look like. And one really nice thing from my experience in developing peer-to-peer systems, distributed systems, is so there's a very clean separation between the networking, the I/O, and the protocol code. So this means that we can do a lot of cool things. So it doesn't, like, the users don't really see this, but essentially the network stack can be swapped out. And since the protocol code is fully deterministic, it allows to do something called discrete event simulation. And that's essentially that we can run simulations of peers connecting to each other, disconnecting, sending filters, syncing the blockchain and everything. And that can all be done in memory without any I/O. So it can be done like, you can run hundreds of simulations or thousands a minute. And that's really helpful to find bugs and things like that. And also very minimal dependencies, because of course it's important to be able to audit things easily. A little bit more on what this looks like. This is just a very small subset, but essentially, the things you can do: you can wait for readiness. You can do a rescan, which is essentially, I want to get the filters within a range. Give it a watch list. You can submit a transaction, of course, and then you can get the channel on the events. And the events are these, amongst others. So you can essentially know when blocks are added or disconnected, i.e. there's a reorg and things like that. So when there's a reorg, you may want to do something differently. And then, of course, when a block matches your watch list, you'll get a block matched event with all of the transactions in the block, and you can update your UTXO set like that. So it deals with transactions, it deals with filters and everything. And so to conclude, sort of what's next and where I'm at with this project. So a lot of things are kind of already pretty stable, working quite well. So all of the kind of basic peer-to-peer networking, connection management, handshake, and all of that stuff, that's working. There's for the address book, there's this stochastic address selection, which is essentially a port from Bitcoin Core. Which again, it's super important for this protocol specifically because we don't want like a bunch of peers pretending that they're different different peers, but actually they're just one attacker, sort of eclipsing your network and then sending you bad filters. So we really need to make sure that the client is always connected to a good selection of peers. Yeah, and then block header, sync, verification, all of that is done, transaction management. And then the compact filter stuff is in a good place. There's one important thing that's missing is a filter verification. And this is not a hard verification, it's a soft verification, or it's a, so it's really this problem of connecting or of checking the filters sent by the peers you're connected to and verifying that they all agree. And if they don't agree, you need to kind of find out who's the culprit, who's lying, who's telling the truth, and ban them. And then and you can tell who's telling the truth or who's lying by downloading the block yourself, the block that the peers disagree on, essentially. It's kind of complicated, that's why I haven't done it yet, but it will get done. Yeah, and that's about it. Thanks. And I'm happy to take any questions.
What kind of, so like in the Bloom filter one,
yeah.
One of the issues was you have a knob to turn for false positives.
Yeah.
And
sorry, you can speak here.
Sure. Yeah, so like with the Bloom filter based, where you have like, you know, a filter per client, you have an ability to change the false positive rate, but either you turn it all the way down, which I think every software implementation did, and you have basically no false positives and completely leak your address, just in a more complicated, annoying way. Or if you have false positives, it actually like sort of was really high and unusable. What is the and it seems like this is better because now you're sort of hiding in a block. If you like, maybe back of the envelope, if you say, okay, I have one address and put that in, like that's what I'm matching against, how many false positive blocks throughout the what percentage or something
with
like that?
With the Galome Rice.
Yeah, like what is it? Because you can obviously target it to whatever you want, but I guess that people have sort of decided, okay, 20 kilobytes is the filter size we're using, and like what does that end up doing?
Yeah. So first of all, the BIP30, so the BIP157 filters don't use Bloom filters, so to speak. They use this new, or not new, but this other filter type called Galome Rice filters, and they were chosen because they were essentially more space efficient. So the false positive rate was lower given a certain amount of data. So that's why they were chosen, and I think it's a very, very low probability, something under 1% of with the new filters. Under 1% of matches will be false positives, basically. So I think it's way under 1%, actually. So yeah, you might download a couple blocks that you didn't need to download. It's possible. On the Bloom filter side, yeah, it's essentially again a trade-off between space and privacy. So you can, if you want to. So on BIP37, you can say, hey, I want extreme privacy, so give me like hundreds of transactions per filter, and then it's going to be very inefficient because all of the proofs are going to have to be included for each transaction. So it's even more expensive than just downloading the block, basically, at that point.
Cool. Okay, and does it scale with number of addresses? Because I guess you have to put all your addresses you're watching. Well, you don't send it; you just sort of match against those each time.
Exactly.
And I guess it would scale sublinear, like So even if you have a lot of addresses, probably it's not really going to affect the false positive rate there.
Yeah, I think it's interesting from it's not, and I think it's there's still a lot of leeway from a wallet implementation perspective to figure out, like, if you don't reuse addresses, then you don't need to recheck them, that sort of thing. But you never know, right? Like if someone mistakenly sends you twice to an address, so it's really up to the wallet to decide if they're going to check all addresses ever forever kind of thing, or if eventually you prune it. But it's I think it's pretty fast to check, and since it's a block every 10 minutes, it's not such a big deal to run through even 10,000 addresses or something every block.
Cool.
Anyone else? All right. Thanks.